If I had to pick one subject as perhaps the most important subject in these first two chapters, I would say, if I had to, I'd say independence. Of course, you could also say everything's fundamentally important too. I mean, the laws of probability are fundamentally important, but I don't know, they're pretty intuitive. Independence is a little less intuitive, but it's really, really important. We use independence all the time for the purpose of modeling. What we often end up doing in pretty much every chapter from this point on, except maybe chapter 6, is we end up, no, yeah, that comes up in chapter 6 too. I think it's pretty much in every chapter. We end up assuming independence in many situations. Independence of events. The book gives you a definition of independence and then a theorem related to independence. I'm going to do the same thing, definition and theorem, but I'm going to switch around what's called a definition and what's called a theorem. Now, I understand the reason why the book did it the way they did. But philosophically, I think it's better to say what I'm about to say as a definition. I'm not going to write the definition very carefully, but the basic idea. Two events, A and B, are independent if the conditional probability of A given B equals the ordinary probability of A, and the conditional probability of B given A is the ordinary probability of B. Now, the reason the book calls this a theorem instead of a definition is because there's an extra technicality that you need in here to actually make this work. This is really assuming A and B are not impossible events. P of A is non-zero and P of B is non-zero. Because if either of those is true, then these conditional probabilities wouldn't make sense, or at least the one, if P of A was non-zero, the second conditional probability wouldn't make any sense because you'd be assuming A has occurred, but hey, if P of A is 0, A can't occur. It's impossible. And for this first one, the conditional probability of A, assuming B has occurred, that would be nonsense if B can't occur, if the probability of B is 0. So because of that little technicality, that's sort of the motivation for why the book calls this a theorem and something else a definition. But I think this just makes more intuitive sense as a definition. In other words, saying what independence truly means. Knowing that B occurs should not affect the chances that A is going to occur. And knowing that A occurs should not affect the chances that B is going to occur. Let's think about it with cards. Well, I mean, you can think about it with flipping a coin. If I flip a coin twice, and A is the event that I get heads on the first flip, and B is the event that I get heads on the second flip, it should be intuitive that those two events are independent if it's a fair coin. It's really an assumption I'm making when I'm flipping coins. I'm really assuming independence. A little less assumption-based is thinking about a deck of cards. What's an example of independent events? How about the event that the card is a heart and the event that the card is a queen? If you know the card, if you shuffle up the deck of cards and you pick out one at random and somebody says, hey, it's a queen, that doesn't affect your assessment of the chances that it's a heart. Doesn't that seem reasonable? And if they say, hey, it's a heart, that doesn't affect your assessment of the chances that it's a queen. It should seem intuitive that those are independent. To be more formal about it, let's compute the corresponding probabilities. The probability of a queen, there's 4 queens out of 52 cards. That's 4 52nds, which simplifies to 1/13. And the probability of being a queen, given that you know it's a heart, is the same thing. You wouldn't write it as 4 52nds, though. Instead, you'd write it right away as 1/13. There's 13 hearts, only one of which is a queen. But these probabilities do simplify to the same thing. They are the same numbers. These are equal to each other. Likewise, the probability of getting a heart is 13 out of 52, which reduces to 1/4. And the conditional probability of getting a heart, if you know it's a queen, there's 4 queens, one of which is a heart, also 1/4. These are equal. So according to that definition, getting a queen and getting a heart as 2 separate events in the one experiment of shuffling up a deck of cards and picking one card out at random, those 2 events are independent. What's an example of non-independent events? I think I did this last time, both examples last time. How about getting a heart and getting a red card? The probability of getting a heart, as we already saw, is 13 out of 52, is 1/4. The probability of getting a red card, or excuse me, the conditional probability of getting a heart, if it is known to be red, is 13 out of 26. 26 reds, 13 hearts and 13 diamonds. 1/2. Not equal. That's enough to say getting a heart and getting a red are not independent. If you know it's red, that increases the chances that it's a heart. And they're not equal the other way either. The ordinary probability of getting a red card is 26 out of 52, 1/2. And the conditional probability of getting a red, if you know it's a heart, is 1, right? You could call it, well, out of 13 hearts, all 13 are red. Don't write 26 over 13 to say the answer is 2. You're focused on the 13 hearts. And these are also not equal. So getting a queen and getting a heart are independent events. Getting a heart and getting a red are not independent events. Did I do all those right? I think so. No mistakes, right? Okay, so that's fitting the definition of independence. That's checking it with the definition. But just as important as a definition is a theorem. And again, the book labels what I'm about to write as a theorem as a definition. And what I wrote as a definition, they call that a theorem. This theorem does even work in the case where P of A or P of B is 0. And that, again, is why the book decided to call this as a definition, so they didn't have to worry about that special case where those could be 0. 2 events, but just philosophically, in most cases, it makes more sense to call this a definition of what independence means. And this a theorem as being something that's actually a little surprising and would take proof. 2 events, A and B, are independent if and only if P of A intersect B is P of A times P of B. This is called the multiplication rule for independent events. And it does work even if one of these events, A or B, is impossible, meaning P of A or P of B is 0. If P of A or P of B is 0, then both sides would be 0. If, for example, A is impossible, P of A is 0. That would also imply P of A intersect B is 0 because A intersect B is a subset of A. An impossible event is independent of any other event. If you know that other event occurs, well, the probability of the impossible event occurring is still 0. And you can't figure out a probability of the other event given the impossible event has occurred because it was impossible. That can't happen. We will use this multiplication rule for independent events all the time. This is effectively what we will use, I think, in pretty much every single chapter, including the chapters on statistics. Well, I guess with the linear regression chapter at the very end of the course, we don't really do much probability, so maybe not there. Though if we went further into the chapter and did some probability, we probably would use it. This is of really, really fundamental importance. How's it used? Again, it's often used. I mean, we can check that it works back here with the cards again. Is it the case that the probability of getting a heart and a queen, in other words, the queen of hearts, is the product of these two probabilities? Yeah, there's only one queen of hearts out of 52 cards, and that indeed is 1/4 times 1/13, the product of these two numbers. On the other hand, with this example, they're not independent. This kind of thing should not be true. The probability of getting a heart and a red is the same as the probability of getting a heart because hearts are red. 13 out of 52 is 1/4. But the product of P of heart times P of R is something different. 1/4 times 1/2 is 1/8. These are not the same. Confirming, since the theorem is an if and only if, it's another way to confirm getting a heart and getting a red are not independent. That's just a verification in this kind of situation. More importantly, how do we use this theorem? Again, we typically use it by assuming independence for modeling purposes. I can apply this with coins. Say I flip a coin twice, flip a fair coin twice. What's the if A is the event that I get a head on the first flip, and B is the event that I get a head on the second flip, what's the probability that I get two heads? Well, that's A intersect B. Both A and B occurred. And well, when we thought about this with the sample space, it was a 4-element sample space, HH, HT, TH, TT. What we did there to get an answer of 1/4 is we just assumed equally likely outcomes. Effectively, that assumption is coming from the fair coin assumption and the assumption of independence, though we didn't call it that. I'm assuming independence, and here's another way to get the answer. As 1/2 times 1/2, 1/4. as a basic use of it. Let's change this to a baseball player. You got a baseball player or softball, if you prefer, has a 300 average, which is pretty good in baseball. Not sure how good that is in softball. Any softball players? Is that a decent average in softball still? Might not be. Maybe 400 is a better average in softball. Well, obviously it's a better average, but a more typical, what's more typically thought of as a good average. If A is the event that the baseball or softball players gets a hit in first at bat, and I'm not worried about technicalities like what if they get a walk. Technically, I should say first official at bat. And B is the event that they get a hit in the second at bat. What's the probability of getting 2 hits? I guess I could write HH again, but I'll just write A intersect B. Independence, the assumption of independence would mean I'd multiply those probabilities and they would both be 0.3. And I get 0.09. If a baseball player has a 300 average, getting a hit about 3 out of every 10 at bats, official at bats, and you know they're going to get 2 at bats in the next few innings, say, what are the chances that they're going to get 2 hits before it happens? About a 9% chance. Pretty small, but still better than somebody with a 200 average, obviously. If they have a 200 average, 0.2, it'd be 0.04 of getting 2 hits and 2 at bats. It's the assumption of independence here. Now, technically speaking, this is computed without knowing who the pitcher is as well, right? The average of a baseball player or softball player is dependent on who they're hitting against. Who's the pitcher? Are they really good or not so good? That could affect the probability of they're getting a hit. So I'm doing this kind of calculation, not thinking at all about the pitcher. If I knew information about who the pitcher was, that could affect the answer because it could affect what these probabilities are, even though they have a 300 average. It is important for us and the rest of class today to talk about something called Bayes' theorem. But before we do that, I want to continue with this baseball example and show you that you can think about this a little bit more broadly using either a tree diagram like we talked about last time or a table. A tree diagram, we've talked about that already, can help you figure out solutions of counting problems. They can also help you conceptualize this kind of situation. Maybe you label the first set of branches, the first at bat. AB stands for at bat. And they either get a hit or they don't. We're ignoring walks, hit by pitch, that kind of thing. So either A or A prime occurs, complement of A, for the first at bat. Then there's a second at bat, where either B or B prime occurs. This is not necessarily the best labeling. You know, maybe it'd be better to use H and H prime for hit and not hit in both columns, maybe. I'm doing the A and the B's based on this labeling up here. And then along the branches, put probabilities. 0.3 and therefore 0.7 right there. A is getting a hit in the first at bat. If there's a 30% chance of that, then there's a 70% chance that they don't get a hit. Again, ignoring walks and things like that. B is getting a hit in the second at bat. There's a 30% chance that that happens, and therefore a 70% chance that B prime occurs. In this kind of situation, it's often helpful to figure out the probabilities of compound events like A and B occurring by multiplying numbers along the branches. And that is using independence. Question?
We have to take into account that they're batting average changes after the first.
Good question, but no, we're going to keep it simple and just assume the batting average stays at 0.3. Maybe it's like their career batting average and it would barely change depending on a given at bat. But yes, what he's saying is correct. Technically speaking, a baseball's batting average will get updated every at bat, whether they get a hit or not. If they get a hit, it'll go up, but if they fail to get a hit, it'll go down. They update it on the scoreboard. 0.3 times 0.3, 0.3 squared is 0.09. We already figured that one out. 0.3 times 0.7 is 0.21. 0.7 times 0.3 is also 0.21. And 0.7 times 0.7, 0.7 squared is 0.49. With 2 at-bats, the 0.09 represents getting 2 hits. That's the chances of getting 2 hits. Again, you have to assess these before they actually take their at-bats. This 0.21 is the probability of getting a hit on the first at-bat, but failing to get a hit in the second at-bat. This one's failing to get a hit on the first at-bat, but succeeding on the second. And this one is failing to get a hit on the first and also failing to get a hit on the second. Notice that these numbers, check it, they do add to 1. Right? These two add to 0.3. Then we're up to 0.51. 0.51 plus 0.49 is 1. If we were thinking about this situation in terms of sample spaces, we'd have 4 outcomes, but they would not all be equally likely. But they do have to add up to 1, the probabilities. This tree diagram is going to be helpful for this Bayes' theorem that I hinted at a few minutes ago, which we're going to talk about in a few minutes. You could also think about it with effectively a table. Maybe put A and A prime across the top row and B and B prime across the leftmost column. The 0.3 and the 0.7 should effectively go in these, you would call these margins of the table. The main body of the table is the internal part here. Main body of the table. And these are the margins. I guess I could include that as a margin as well, but I'm kind of separating it from the other ones. The 0.3 and the 0.7 should go in those margins. 0.3 under A and 0.7 under A prime. 0.3 to the right of B and 0.7 to the right of B prime. With the assumption of independence, we fill in these 4 slots in the main body by multiplication. What goes there? 0.3 times 0.3, 0.09. What goes here? 0.3 times 0.7, 0.21. What goes here? 0.7 times 0.3, 0.21. And what goes here? 0.7 times 0.7, 0.49. Not only does this column add up to 1 and this row add up to 1, but all the numbers in the main body also add up to 1. So it's another way to visualize what's going on. I will tell you that this kind of point of view is essential when we get to chapter 5. And we talk about random variables that are really random vectors, multivariable. And there's chapter 5 is where a little bit of multivariable calculus comes into the class, even though we don't make that an official prerequisite. We do it at an easy enough level that even if you haven't had multi, that you can still learn it. Okay. We're going to be talking about what are called joint distributions, and joint distributions, which correspond to the main body, have what are called marginal distributions. And the numbers in the middle are found by products when we assume independence. There are going to be some joint distributions where we do not assume independence and we'll have other numbers in there. But they still have to add up to the numbers in the margins appropriately.